Welcome to Chapter 5. We are going to be looking at the EM spectrum and other things that have to do with light. Let there be light. And the image that you're seeing behind me is actually a spectrum off of the sun. And we'll talk about what those lines mean and why it's broken into these different things along the way. Some of it we'll talk about today, and some of it we'll talk about in a later lecture. But let me go ahead and see if I can get everything up and running here. Try to share my screen with you so that we can see what's going on here in our PowerPoint. And can I start the slideshow? Yes, there we go. Radiation and spectra. When I talk about light, it can actually mean two different things. It can mean what we see, Roy G. Biv, which is the spectrum that you're seeing back here, red, orange, yellow, green, blue, indigo, violet, all the way down the colors of the rainbow. Or if I talk about light more generally, it can talk about all of this as well as the stuff that we can't see, but is still being generated, is still being radiated from the sun and other objects. That includes ultraviolet light, that includes infrared. Ultraviolet means anything below the blue spectrum, and we often talk about that as actually being higher rather than lower because it's higher energy stuff. And infrared is stuff that is beyond the red there, and that's typically lower energy stuff. So if you sort of keep that in mind, blue equals higher energy, red equals lower energy. That will help you in a number of different ways, including whether things are coming towards you or going away from you. If it's coming towards you, it has more energy coming towards you. The light has more energy, and therefore you get a blue shift. If it's going away from you, it's sort of being pulled away. And it has a red shift along the way. When I say it gets more energy or less energy, I'm speaking more colloquially than I am speaking in precise terms, but close is good in astronomy, so we're going to go with it. When we look at the sun, don't look directly at the sun, but when we look at the sun, we can see a lot of different things coming off of it depending upon how we're looking at it. And this picture here shows you what the sun would look like if we could see it in infrared or ultraviolet. This particular one is in fact ultraviolet. Infrared has a different kind of glow, but one of the things that would be consistent with it in infrared is we would have different kinds of markings, different kinds of areas on the sun, the way we do with this one in the ultraviolet. The sun actually puts out most of its energy, the peak of its energy, in Roy G. Biv, which we have being represented by my backdrop here along the way. One of the guys we can credit for figuring out all of these different things that are tied together is James Clerk Maxwell. He's not the only one. He's a link in a chain, but he's a major link. And one of the things he figured out is not only do we have all of these different bands of light that come together, but they're also tied into magnetism. He sort of figured out that as he was working with equipment and with equations, that the things looked very similar. Now, for a very long time, there was a debate on whether or not light was a wave or a particle. And we had a party over here that was the wave party and a party over here that was the particle party. And they would fight back and forth, literally fisticuffs at some points in the history of science. You wouldn't think that a bunch of science geeks would take that much to heart, but in fact they did. What we now know, of course, is it's some of both. But when we're talking about waves, we're just talking about standard waves like you would have in a pond here. We see the frog generating some waves as they go out. Notice they expand out. They have less and less intensity as they go out. That's going to be important for us to understand as well. When we're talking about waves, nothing complicated here. We have a top and a bottom and a midpoint. The top of the wave is called the crest. The bottom of the wave is called the trough. We can measure it from crest to crest, top to top, or bottom to bottom, trough to trough. We can also do a midpoint measurement, but if we do that, we have to be sure that we're measuring 3 rather than 2, because to get back to the same point in the wave, it's going to be 3 different points. Now, why would we need to do that when we could just do the top or the bottom? Well, if it's coming through an aperture or a slit where there might be something being cut off, you might want to measure it in the midpoint there. So there are some different kinds of things. Typically, light goes at a consistent speed we call c. And when we talk about c, we typically talk about it in terms of how fast it goes in a vacuum. The reason why I'm saying typically here is because we can actually slow down the speed of light if we put it through a substance, if we put it through water, if we put it through a crystal or something like that. But even when we do that, it will be consistent in its speed in those things. So that becomes an important thing to know. The speed of light is a constant, but it can vary depending upon whether it's going through an atmosphere or whether it's going through a crystal or something else. Now, to get our speed of light, which we often use the lowercase c to represent, we multiply wavelength, how long the wave is, times the frequency, how many of them there are, which basically means when you adjust one of those up, the other one goes down, so they stay in balance. So knowing the value of c is a very important thing. And the value of c is basically 300,000 kilometers per second. And I like to use the metric system here because it is easier to multiply. So 300,000 kilometers per second. It's also 186,000 miles per second. That's the one that we mostly know. And of course, these are approximations, but close is good in astronomy. Close is good with the speed of light as well. That's insanely fast. The moon is a little over a second and a half away when we're talking about this kind of speed of light there, but it's not instantaneous. Light doesn't just start somewhere and get somewhere else instantly. It does take time. The sun is about 8 light minutes away, because if we talk about the sun being 93 million miles away, well, 93 million miles divided by this gives us about 8 minutes. Basically means if the sun blew up 6 minutes ago, we wouldn't know for 2 more minutes. Not exactly a comforting thought. We also have amplitude, which is an important distinction in the waves. If you have a radio, you might have AM, that's amplitude modulation. You might have FM, that's frequency modulation. The size of the wave, up and down here, the frequency, the number, those can be adjusted. For our purposes, we won't deal too much with amplitude, so I wouldn't worry too much about that, except to know that that's one of the things that is a factor, part of the properties of waves. When we are dealing with these things, we actually know that the speed of light includes Roy G. Biv, includes ultraviolet, infrared, X-rays, gamma rays, radio waves, microwaves, also includes the magnetic field kind of thing. And that's why we call these electromagnetic waves. And all of these things bind together and they go at the speed of light. Now they've given you here 3 significant digits, 2.99 times 10 to the 8th, and this is meters rather than kilometers per second there, but it still averages out to 300,000 kilometers per second. Here we can see the whole expanse of our electromagnetic spectrum as we use it in astronomy. We have our radio waves, which are longer. A radio wave, a single radio wave, can be as long as a football field. So one wave can take the entire length of that. They are very, very long. Notice here we have microwaves. Now microwaves, you would think with the prefix micro, that it would be small. Well, it's small compared to standard radio waves, but in fact, it is much longer than our visible light waves. Typically, everything over here, including our infrared, is lower energy. So if it's going through you, it won't hurt you. Now, you may be stopping me and say, but wait, microwaves can be dangerous. The reason why microwaves in your microwave oven are dangerous is not because of any individual microwave. Any individual microwave not going to hurt you at all. It's because they're intensified so that it will heat up your objects inside. So you don't want to climb in the microwave and use that as a substitute for a tanning booth, for example. But infrared waves, not really going to hurt you. Radio waves, not really going to hurt you. Microwaves, a single microwave is not going to hurt you, just in the way that visible light typically won't hurt you. But if you go out and get a sunburn or you get overheated, you're getting intensity from ultraviolet, visible, and infrared lights over here. X-rays, on the other hand, notice as we get shorter and shorter and shorter, we get more and more energy, we get more and more intensity from a single ray. If you've ever gone to the dentist office, what they do to you is they sort of wrap you up like the Michelin Man, and then the attendant moves out of the office and then goes and presses a button for just a minute and then comes back and pulls it out of your mouth, and there's saliva going everywhere, and you're like, oh well, that one didn't work, and they have to do it again. It's like, oh. So one single X-ray can really do some damage. A lot of X-rays can do a lot of damage along the way. So the further away we go up in this range here, the more damaging the rays can be, the more energetic a single ray can be along the way. So X-rays were sort of discovered by accident. Gamma rays were sort of discovered by accident. Infrared was in fact discovered by accident, because none of these things are visible to the naked eye. And the dangers attached to X-rays and gamma rays and radioactive materials were sort of discovered by accident. Marie Curie, she was one of the ones who won a Nobel Prize for working in this area. Her notebooks and other things that she had during her life are still radioactive and will be radioactive for a long, long time to come. They're in sort of lead-cased kinds of displays, so that the people going to look at them don't get a dose of the radiation that's coming off of this stuff. Nobody knew back at that time along the way. They used to use X-rays in shoe stores to X-ray your shoes. It was a marketing thing. They had these boxes made out of cardboard and wood, and they would, instead of just the little zzz that the dentist office does, they would just sit there and chat with the parents of the kids as they were being dosed by X-rays, because they didn't know you just had to have just one short burst. And of course, lots of shoe salesmen died of cancer because there was no shielding. Most of the time, even though there was a heavy dose of X-rays, it was a one-time thing for kids and parents, the shoe salesmen were getting it over and over and over again. In terms of the radiation, like I was talking about Marie Curie, radium, they thought, oh, hey, this glows in the dark. So they mixed it up into paint. And women in the Netherlands, quite frequently, they were doing this in the Netherlands in the watchmaking industry there, would paint using radium-enhanced paint. They would grind up the radiation. They would grind up the radioactive material and put it into the paint. And then they would paint on the watch dial so it would glow in the dark. Hey, that's neat. But they would take their paintbrush and lick the tip, and then paint on the dial, dip it in the paint, lick the tip again, and paint more. If you've ever seen anyone with cancer of the jaw from chewing tobacco or something like that, that's what was happening. We find out things quite frequently by trial and error, and often by accident that way. But again, light, we have our wavelengths, we have our amplitudes, we have our frequency. When we're talking about the colors of light, whether it's red, orange, yellow, green, blue, indigo, or violet, or beyond the red, infrared, or beyond the violet, ultraviolet, we're talking about wavelength. So notice here, red light is about 700 nanometers, very, very tiny. Blue light is 450. So that's a big drop just in this little rainbow area where I'm sort of sitting along the way. So when we're talking about ultraviolet, we're getting much less than this. They get shorter and shorter and shorter very quickly. Radio waves get longer and longer along the way. But a single ray of light, in terms of Roy G. Biv, what we could see, if I put my fingers together, one ray would fit in the empty space between my skin cells as I'm putting my fingers together. It is that small. So fortunately for us, our atmosphere on the planet actually blocks most of the radiation that's coming off of the sun and elsewhere in the universe. As you can see here, Roy G. Biv mostly makes it to the surface, not all, some of it's blocked. A little bit of UV makes it through, a little bit of infrared makes it through, more infrared than UV. Radio waves don't tend to have a problem. They go through a lot of stuff along the way. Microwaves and some infrared get blocked over here. Fortunately for us, most gamma rays and X-rays and other things that can be real killers actually get they get blocked quite significantly too. Here's another look. Notice the visible light is coming through. Notice it has this little obscuring. It's not just plain sailing all the way down to the ground. That's why we often put observatories at the tops of mountains, because we're trying to get away from the atmosphere. And the further up you go, the less atmosphere there is. Radio waves don't have to worry about that. Infrared, we have these different pockets where stuff comes down. So we will have different observatories that we can put on planes and fly up here. We want to look at gamma rays and X-rays and ultraviolet. We typically need to go out into space. And of course, to get away from the atmospheric interference, we also go out into space. And that's where the Hubble comes into play. And we will talk more about that in chapter 6 a little bit later. I'll be recording that video right after this one. When we are able to get out into space, we see that there's a lot of stuff that's out there that we wouldn't be able to see or know from the ground level. X-rays in particular. Here we can see a cross-section of our Milky Way galaxy, our collection of stars that we live in, from an X-ray perspective. We have different ranges of X-rays, just like there's different ranges of visual light, Roy G. Biv, there are different ranges of X-rays, or more energetic and less energetic X-rays as well. So we can see that there are different kinds of things happening out there. And you may remember the movie Alien with Sigourney Weaver, "In space, no one can hear you scream." That was their tagline. Well, if you could hear in X-rays, if just by some miracle you could start hearing in X-rays, you would find out that space is a very, very noisy place. There's a lot going on out there. Now, when we break the light that comes from the sun apart, and that's sort of what you're looking at when you're looking at my backdrop here, we call this a spectrum. And we can get that in different ways. We can get that through oil. We can get that through water. That's how we get rainbows. The light is being refracted through the water droplets. And we can get it through prisms or other kinds of substances. So we can break it into a rainbow, and we can break it into a way of looking at the longer waves around the red and the shorter waves around the blue. And this was one of the ways in which the infrared was first discovered. There was someone who was taking readings here. In fact, it wasn't just someone, it was our guy, William Herschel. Remember in a previous lecture, I talked about going to his house in Bath in England. Well, he's the guy who sort of had a thermometer over here, but didn't know that there was any light happening over here, because all he could see was this, and this thermometer was going up in temperature for no good reason, because he didn't think there was any light hitting it. And that's when he discovered there's more than meets the eye. That's an important thing. As light goes through something like a water droplet or a prism or something like that, what's happening is it's being split apart. So we can see the rainbow effect that's happening here. We have the shorter waves that are going this way, the longer waves that are going this way. These are more energetic down here. These are less energetic up here, but they're getting through in the same time. So that's the important thing to understand, because the speed of light is still the same. Our sun puts out the majority of its light right at the middle of the visible range. It does put out some ultraviolet, but not as much as the visible light. It does put out some infrared, but not as much as the visible light. There are some stars that actually peak over here. They put out most of their light in infrared. They look reddish to us because that's the closest light we can see to what it's putting out. There are some stars that put out a lot more energy in the blue area. They look bluish to us because, again, that's the closest light that we can see. But this whole sort of slope kind of thing, we see this rise and slope. This happens with pretty much everything. The colder an object is, the further down here it's going to be. Your human body, for example, is going to be down in this range over here because you are putting out infrared light. This is how Silence of the Lambs works. If you think about the end of the movie where they're doing the night vision goggles along the way, your body puts out light, but it doesn't put out Roy G. Biv. It puts out infrared down here. Unless something's at absolute zero, it's putting out something. This whole thing is called Weans Law and the Stefan-Boltzmann Law. And I'm not going to make you do anything with these calculations here, so don't worry about that. But I do want you to know that there is actually math behind it. And it's not terribly complicated math. You can see there are only a couple of variables at play in both of these along the way. But essentially what happens is the hotter something is, the further and further up it goes in intensity over towards the blue. So you can even play around with this. If you have a coil kind of stove, you turn it on and it goes through a sort of different color, the red, and then it goes into orange, and then it sort of gets into if you have a hot enough stove, a white light. You can watch that happen as different things burn on our planet as well. They go through different intensity levels with these things. And this, of course, is the spectrum of our sun, hence the backdrop that we have here. What's happening here are these lines are indicative of atoms in the sun of different elements. Most of the atoms in the sun are hydrogen. The second most abundant element in the sun is helium, but there are traces of other elements throughout the sun as well, and that's part of what we're seeing here. And there's a way of figuring all that out. What happens is different elements have different structures inside of their atoms, and the atoms will have a particle in the middle called the nucleus that's made up of protons and or neutrons, and neutrons, not or, but sometimes just protons, usually protons and neutrons, unless it's pure hydrogen, which basically will be sort of pure basic hydrogen is just one proton and one electron going around. But what happens is that electron going around is sometimes a little bit closer in and sometimes a little bit further out from the nucleus, and as it either energizes or sheds energy, it will emit or absorb light according to those areas, because it doesn't just sort of go along in a spectrum. What it does is it jumps from one level to the next, and these are indicative of the jumps. Notice hydrogen here, our second line below the continuous spectrum, has 4 particular lines. We call these the spectral lines. So its atom has in its electron going around 4 different places it can jump back and forth. Notice some are much more complicated, some are more simple along the way. We can get a spectrum in different ways, as I mentioned before. Rainbows, here's a wonderful picture of 2 different rainbows happening at the same time. Notice the sunlight goes through the water droplet and comes out, and the water droplet's acting like a prism. So you can get this effect when you have moisture in the air. You often get it when we're having rainstorms or mist, or fog will often do this. Whenever you have water droplets, this can happen. But it also depends upon the angle you're looking at. You won't necessarily see a rainbow from over here if you're looking in this direction. So that does make a difference. What happens when light spreads out from something like the sun or anything else that emits light or reflects light? This happens with emitted light or reflected light as well. We have what's called the inverse square law. And this is the same square law that worked for gravity. So light works in the same way as gravity. The further away you are from something, the less attractive it is gravitationally. The further away you are from something, the less bright it is from the light. And they fall off by the same inverse square. So if you're twice as far away, notice you've got 1/4 of the light. If you are 3 times as far away, you've got 1/9 of the light. That you would also have 1/4 of the gravity and 1/9 of the gravity that's happening there along the way. So within the atoms themselves, we often see this kind of system here set up. We have the proton in the middle. It's got a plus. We've got electrons going around. They're negative. That's a minus. Ernst Rutherford figured out as he was beaming particles through that there's a lot of empty space here. Sometimes it can just go right through and not hit anything, or go right through and not hit anything. Sometimes it's going to hit the middle, sometimes it's going to hit one of the electrons, but there's a lot of empty space in here. And if this were the actual size, what you're seeing here on the screen, if this were the actual size of the nucleus of an atom, chances are these electrons would be orbiting out past the moon. I mean, there would be 100 to 200,000 miles, maybe more, between those, depending upon what shell they're in along the way. So there's a lot of empty space there for things to hit. Hydrogen atom, again, most simple one there is, proton in the middle, electron going around. This is a little bit misleading to look at it here because they're three-dimensional. So it's not just a flat kind of thing going around. It's actually going around every which way. So think about it as a shell, like almost a globe around as it goes around. Helium is the second element. Hydrogen is number one. Helium is number two. If you remember your big chemistry chart, the periodic table, hydrogen's up in the corner for number one. Helium's over here for number two. It's number two because it's got two protons, but notice it also has two neutrons. So it's actually got four particles. It's got two electrons because it has two protons. They balance each other out along the way. Helium was discovered on the sun before it was discovered on the Earth by looking at these different lines that are here, because it was giving us a feedback from the spectral analysis that we didn't recognize from different elements here on Earth. You can have variations on a theme. Here's all three of these are hydrogen. That's why they've all got H, because they've all got one proton and one electron. But you can have some extra particles inside. And this extra particle is a neutron. It's neutral. It's not plus or minus, and it also doesn't affect whether or not it is hydrogen along the way. But most hydrogen, by far, is going to be this one over here on the left. These are at play in different kinds of experiments, and if you ever hear about heavy water experiments, they're using hydrogen that has neutrons in the nucleus. Some of the guys who helped us figure this out are Niels Bohr and Max Planck. Niels Bohr is actually a favorite character of mine in the history of science because when he was doing many of his experiments, he became world famous, he won awards. But one of the things that he won that I think a lot of people might not really appreciate as much as they should is the breweries in Denmark admired him so much that they gave him a house next to their brewery, and he had beer on tap directly from the brewery. They admired him so much there. He was also a hero in World War II for helping to get people out of Denmark during the Nazi occupation along the way. Max Planck is one of the more brilliant figures in 20th century nuclear physics, and astronomers owe a lot to Max Planck figuring out how we can understand things like this and other things that are coming off of stars along the way. In particular, Niels Bohr helped us understand that we have these different shells inside. So again, we don't just put energy into something and it goes continuously along. It actually jumps from level to level, and it will go as it gets more and more energy, as it absorbs energy, it'll jump from one line to the next, to the next, to the next. As it gives out energy, it will sink back down along the way. And there are lots and lots and lots of different kinds of energy setups that we can talk about inside of elements. I'm not going to hold you responsible for this because it takes a lot of physics and a little bit of math to understand what's going on inside here, except to realize that in fact what's happening is we have absorption and emission happening. When it absorbs energy, when the electron absorbs energy, when the atom absorbs energy, the electron will jump to a higher state. And therefore, if you're looking at it, it will actually leave a dark line because it's absorbing the energy away. If it's emitting the energy, then it's going to give you a bright line which is there. And the electron itself will jump to a lower level of energy along the way. And that's why we sometimes have these absorption spectra. That's what this is called here, over here on the right. Notice we have the lines missing. That's because as energy is going through what we're looking at, say here this is a gas cloud, we are in fact losing those bits of energy. If we were looking at the gas cloud and what it was emitting by itself, notice we have a similar pattern that's happening here along the way. So we do have an emission spectrum here. If we're just getting the continuous spectrum without any of that kind of interference, that's the third kind. So there are 3 kinds of spectra, and I think there's probably a quiz question on this. And the 3 kinds are called the absorption spectrum here. Here's the word absorption in your write-up here. We have the emission spectrum here, the bright line. Here's the word emission here. And then we have continuous. So absorption, emission, and continuous. Those are your 3 types of spectra that are happening here. But these waves are also affected by the Doppler effect, just in the same way that waves as sound waves are affected. If you're sitting next to a police car or a fire engine or an ambulance or something like that, and the siren is going, you're going to get a consistent sound, whoop, 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 whoop kind of thing. I'm not a good mimicker of that, so bear with me. If it's coming towards you, however, like our person down here on the right, if it's coming towards you, it will sound like it's got a higher pitch. If it's going past you, if it's going away from you, it will sound like it has a lower pitch. How many of you have ever been in the car, you're driving along and the lights go on and the siren goes on and you're like, oh no. And then as you begin to pull off because you're a good citizen and you're not going to go Dukes of Hazzard on them and try to outrun them on I-69, as they go past you, the sound shifts and you're like, oh, thank you. That's not just the sound of relief. That is, in fact, as the police car was coming towards you, the siren is putting out waves, but it's already put out waves and it's putting out more waves into those waves. So it's pushing up the waves. It's actually pushing it into a higher pitch. As it's going past, it still has the waves out there, but it's putting out more waves, but it's pulling away from the waves. So they're actually acting like a baffle, and it, in fact, lowers the pitch. So it does actually sound higher as it's coming towards you, sounds lower as it's going away from you. Train whistles are a great example of that. If you're sort of sitting at the railway track waiting for the train to come along and they have the whistle as it's coming towards you, it's a higher pitch. As it's going away from you, it's a lower pitch. Light does that as well. If something is moving away from you, again, redshift. Remember, if it's moving away, lower energy, it's going to be a redshift. If it's coming towards you, down here at C, it's blue shifted. Notice these lines that are here. See, if it's just sitting there, it's giving you the lines. But if it's coming towards you, they're actually being pushed a little up towards the blue. Notice all of these lines have shifted a little bit towards the blue. If it's moving away from you, it's actually being shifted towards the red. This one's over here, this one's over here. And that's the good old Doppler effect. We can actually see that happening also when things are revolving. If something is revolving around the side that's coming towards you, the light gets a little bit of a kick and it gets a little blue shift. As it's going away from you on the other side, it's getting a little tug, it's getting a red shift. So when we see that happening, we see a blue shift over here and a red shift over here. We can tell the direction of the spin. We can do that with the sun as well. That's the good old Doppler effect. And I think that's it for our lecture on this. So I will see you with a different kind of backdrop here shortly on our chapter 6.